In Module 6, we spent a lot of time talking about equilibrium processes, but we focused specifically there on solubility equilibria. We're going to continue talking about equilibrium in Module 7, but now we're going to shift to acid-based equilibrium. And you did study acids and bases in your first year course, and in this course, we're just going to go into quite a bit more detail about acids and bases. Now, the first thing we want to do is hit a definition of acids and bases, again, which you probably remember some from your first year course. There is more than one definition for acids and bases, and we will delve a little bit more deeply into that at the end of the module. For right now, though, what we're going to use is the Bronstead-Lowry definition, which is that an acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. And in some books, you will see that they word that as a proton donor. And the reason for that is if you think about the atomic structure of a hydrogen atom has one proton in the nucleus and then one electron in the electron cloud outside of it. And so if it loses that electron, you don't have anything left but a proton. And so that's why some books will call it, instead of a hydrogen ion donor or an H plus donor, they'll call it a proton donor and a proton acceptor instead. Now, your book doesn't talk about strong acids and bases and weak acids and bases until the next section, but I think it's helpful to talk about it at the beginning. And again, you have talked about this a little bit in your first year course, but I want to review it. So don't be surprised when you hit it again in the next section when you read that tomorrow. So a strong acid is one that dissociates completely, which means you're going to have a complete reaction. You're just going to have a single arrow going to the product side, and there's not any kind of equilibrium that is set up if you have a strong acid or a strong base. The strong acids you will need to have memorized, and so your strong acids are made from 3 of the halogens. You'll remember that hydrofluoric acid, we talked about that earlier. We said hydrofluoric acid is actually not a strong acid because the hydrogen bonding with the fluorine is so strong. And so hydrochloric, hydrobromic, hydroiodic acids are all strong acids, as well as nitric, sulfuric, and perchloric acid. There are some books that will also classify just chloric acid as a strong acid. These are the 6 that the author of this textbook expects you to know, and so that's what I'm expecting you to know also. So you do need to have those memorized. And then strong bases, which will dissociate completely, are any hydroxides that are made from the 1A column of metals. So lithium, sodium, potassium, and anything in that column that you make a hydroxide out of, that will be a strong base, as well as if you have the hydroxide of the ammonium ion, so NH4OH, that will also be a strong base. Everything else is a weak base and will only dissociate partially and set up an equilibrium, okay? So that kind of gives you a heads up. He'll talk about it in the next section, but you do have to have these things memorized because you're gonna have to be able to work problems knowing whether you're dealing with a strong acid or base or a weak acid or base. Okay, so that's the difference between strong acids and strong bases. Just like we had a solubility product constant when an equilibrium was set up when something was dissolving, we also have what's called an acid dissociation constant or a base dissociation constant for acids and bases. So in this reaction up here, I'm looking at acetic acid, which is the acid that's found in vinegar. Some acids, you're going to find them written as COOH, and so this H at the end is what pops off, and so this pops off and adds to the water to give us a hydronium ion, which is something you should recognize, and then this becomes the negative ion of that. And so just like when we write any ionization constant, I probably should have written in here the phases of these. This one would have been aqueous, water is a liquid, and then these ions are also going to be aqueous. And as you will recall, we don't include the formulas for solids and liquids in an equilibrium constant expression. So everything else except for the water is going to be included here. You'll remember that products go on the top. So the acid dissociation constant for acetic acid is going to be the concentration of CH3COO minus times the concentration of H3O plus, and all the coefficients are 1, so obviously I don't have any superscripts, and I'm going to divide that by the concentration of acetic acid. And all of those, just like before, are going to be expressed in moles per liter, so there's nothing different there than what you've already learned. So that's an acid ionization constant. We also have, with acids and bases, what we call a conjugate acid-base pair. So if I look here, according to the Bronstead-Lowry definition, this is the one that's donating the hydrogen ion to the water. So in this reaction, this one is the acid, and this one is the base. Now, with the conjugate acid-base pair, I'm looking at what's on the other side. A conjugate acid and base pair are related by a hydrogen ion. So if this is the acid, this is the same thing, except the hydrogen ion is now gone. And so this is classified as the conjugate base, and the hydronium ion is classified as the conjugate acid. The other way to think about that is if you would take the reaction and run it backwards, which one is donating the hydrogen ion? So if I run the reaction this direction and go this way, the hydronium ion would be donating the hydrogen, one of its hydrogen ions, to this base. And so since this is the hydrogen ion donor, if I run the reaction in reverse, this is the acid and this is the base. So you can think about it either way. You can think about it by saying, okay, this and this look almost the same, except one of them has a hydrogen ion missing. Okay, so you can think about it that way. And the H2O and the H3O plus are the same way. They're the same formula minus a hydrogen ion. Or if you run the reaction backwards, which one is acting like the acid, which one's acting like the base. Okay, so there's your acid ionization constant. You'll see it looks very much like a KSP. The only difference is that because the acid is dissolved in water, that I have to take into account that concentration down in the denominator. Okay. Similarly, I could look at a weak base like ammonia, NH3. That's different than this, so don't confuse NH4OH, which is actually a strong base, with NH3, which is a weak base. They look similar, and they both smell bad, but they're not the same thing. So this one acts as a weak base, and just like I had up here where I had a double-headed arrow going in both directions, an equilibrium is going to be set up here. So if I examine this equation, the water in this case is the one that's going to donate the hydrogen ion to the ammonia, because I end up with NH4 plus over here. So in this case, since this is the hydrogen ion donor, this is the acid, and this is the base, okay? Then, again, think about it whichever way is most helpful to you. The NH3 and the NH4 plus are the same formula with the exception of an additional hydrogen ion. So if this is the base, that means that this one is the conjugate acid. H2O and OH minus are also related only by the difference of a hydrogen ion. So if this is the acid, that makes this one the conjugate base. Again, the other way to think about it here is if I take the reaction and run it backwards, which one donates the hydrogen ion? The NH4 plus is donating the hydrogen ion this direction, and so it's going to be the conjugate acid. So if I look at conjugate acid-base pairs, in this reaction up here, the CH3COOH and the CH3COO minus are a conjugate acid-base pair, and the H2O and the H3O plus are a conjugate acid-base pair. In the bottom reaction, I would have NH3 and NH4 plus as one conjugate acid-base pair, and then I would have water with a hydroxide ion as a conjugate acid-base pair, okay? I could also write a base ionization constant, or I would have a base ionization constant. I could write an expression for this as well. And there would be numbers associated with these. You can look these up in reference tables. You can find them online. So if I'm going to write an expression for Kb from my ammonia, I'm going to have NH4 plus times the concentration of OH minus over the concentration of NH3. Okay, NH3 is most often a gas, but you can take a gas and you can dissolve it in water. And so this would have been aqueous, this would have been a liquid, and then these guys would have been aqueous as well. All right. Now you'll notice that in this reaction, the water acted as a base. In this reaction, the water acted as an acid. And so the term for that is amphoteric. And in some books, you will find it called amphiprotic. Means the same thing, and that just means that it can act either as an acid or as a base. You may be asking yourself, well, how can I tell if water is going to act as an acid or a base? And we'll get to that a little bit later in the chapter, and so I'll explain that later to you as to how you're going to be able to tell which one's going to act as the acid and which one's going to act as the base if it's not a relatively obvious thing there. So if we look at example 7.1, they are asking us to determine the conjugate acid for, I'm just going to put a little box here in the middle so that it doesn't get too mixed up with everything else, for SO4 2 minus. So they're asking us what is the conjugate acid for that. If this is the base, the conjugate, this is the base, then that means it's going to accept a hydrogen ion. So that means that the conjugate acid is going to be this plus a hydrogen ion. So it's going to be HSO4 with just a -1 charge now. Because if I've added an H plus, the -2 is going to go down to a -1. Okay? So they're conjugate acid base pair related just by the addition or subtraction of a hydrogen ion. Part B says, what is the conjugate base of HNO3? Well, if I'm looking at the conjugate base, I'm looking at what is this after it's lost a hydrogen ion. So the conjugate base is going to be NO3 minus. Okay, so make sure you get your ion charges on there. All right, so you will have some practice today with learning conjugate acids, conjugate bases, and determining what those are for some compounds that they give you.